Hello students, welcome to MJC Learning. I am Manju Dilip. Today I am going to start with the 12th standard mathematics topic differentiation part 9. We already studied in the previous video about implicit differentiation and we solved some questions. So today again we are solving some more questions from implicit differentiation and discussing about derivatives of parametric functions. So the first question is, if log x plus y is equal to log xy plus p, where p is constant, then prove that dy upon dx is equal to minus y square upon x square. So we are starting with the question, log of x plus y is equal to log xy plus p. Then log xy can be written as log x plus log y plus p using this law. Then differentiating both sides with respect to x, we get 1 upon x plus y into 1 plus dy upon dx, because the derivative of log of x plus y is 1 upon x plus y, and since it is not x, you have to take the derivative of x plus y. So derivative of x is 1 and derivative of y is dy upon dx is equal to derivative of log x is 1 upon x, derivative of log y is 1 upon y dy upon dx. Then next step we are expanding this one. So 1 upon x plus y plus 1 upon x plus y into dy upon dx is equal to 1 upon x plus 1 upon y dy upon dx. Then in the next step here it is collecting the derivative terms together. So 1 upon x plus y minus 1 upon y into dy upon dx is equal to 1 upon x minus 1 upon x plus y. Taking LCM, so y minus x minus y upon y into x plus y into dy upon dx is equal to, here again taking LCM, so x plus y minus x upon x into x plus y. So y minus y cancel, x minus x cancel, so we'll get like this, minus x upon y into x plus y into dy upon dx is equal to y upon x into x plus y. Now x plus y and x plus y cancelled from the denominator. So we'll get minus x upon y into dy upon dx is equal to y upon x. Now cross multiplying, dy upon dx is equal to minus this y will come into the numerator. So y square upon x square. This is the final answer for this question. Next question is, if sine inverse of x raised to 5 minus y raised to 5 upon x raised to 5 plus y raised to 5 is equal to pi upon 6, show that log x plus y is equal to x raised to 4 upon 3 into y raised to 4. So we'll consider sine inverse of x raised to 5 minus y raised to 5 upon x raised to 5 plus y raised to 5 is equal to pi upon 6. In the next step, we'll take this sign to the right hand side. So x raised to 5 minus y raised to 5 upon x raised to 5 plus y raised to 5 is equal to sine of pi upon 6. Sine pi upon 6 is value is sine 30 is 1 upon 2. So we are substituting that value here. Cross multiplying, 2 into x raised to 5 minus y raised to 5 is equal to 1 into x raised to 5 plus y raised to 5. Now in the next step it is multiplying with 2 into x raised to 5 minus this x raised to 5 is taken to the left hand side. It will become minus x raised to 5 is equal to 2 into y raised to 5. This is minus 2y raised to 5. That will come to the right hand side. So it will become positive. So 2y raised to 5 plus y raised to 5. So 2x raised to 5 minus x raised to 5 is x raised to 5. That's equal to 2y raised to 5 plus y raised to 5 is 3y raised to 5. Now taking derivative of this term. So this is x raised to n format. So derivative of x raised to n is n into x raised to n minus 1. So 5x raised to 4 is equal to 3 into 5y raised to 4 into dy upon dx. 5 cancelled. So x raised to 4 is equal to 3 y raised to 4 into dy upon dx. Therefore dy upon dx is equal to x raised to 4 upon 3 y raised to 4. This is the final answer for this question. Next question is, if x raised to y is equal to e raised to x minus y, then show that dy upon dx is equal to log x upon 1 plus log x whole square. So we'll consider this question, x raised to 5 is equal to e raised to x minus y. Taking logarithm on both sides, we get y log x is equal to x minus y into log e. We all know the value of log e is 1. So I am substituting that value here. So y log x is equal to x minus y into 1. Then in the next step, we can take this y to the left hand side. So y log x plus y is equal to x. Can take this y outside. So y into 1 plus log x is equal to x. Now y is equal to x upon 1 plus log x. Now I'll take the derivative with respect to x. So differentiate with respect to x. We'll get, this is derivative of u upon v format. So derivative of u upon v is equal to v du upon dx minus u dv upon dx upon v square. So in the place of v it is 1 plus log x. So 1 plus log x into derivative of x is 1 minus x into derivative of 1 plus log x is derivative of 1 is 0. Derivative log x is 1 upon 1 plus log x whole square. Now that is 1 plus log x minus x into 1 upon x. X cancel, so minus 1 upon 1 plus log x whole square. That is 1 minus 1 cancel, so log x upon 1 plus log x whole square is the answer for this question. Next question is, if y is equal to root of log x plus root of log x plus root of log x plus etc. infinity, then show that dy upon dx is equal to 1 upon x into 2y minus 1. So solution will take this function y is equal to this function as equation number 1. So in the next step, we can change the remaining terms from this term to remaining terms till infinity. We can take y. So y is equal to, the given question will become y is equal to root of log x plus y. Now squaring both sides, we get y square is equal to log x plus y. Now differentiate with respect to x. 2y dy upon dx is equal to log x derivative is 1 upon x plus dy upon dx. dy upon dx into 2y minus 1 is equal to 1 upon x. So dy upon dx is 1 upon x into 2y minus 1. This is the final answer for this question. Next question is, if y is equal to x raised to x raised to x raised to etc. into infinity, then show that dy upon dx is equal to y square upon x into 1 minus log x. Considering this question as equation number 1, therefore the next step we can write it as y is equal to x raised to y. So taking logarithm on both sides, log y is equal to y log x. Differentiate with respect to x. Log y derivative is 1 upon y dy upon dx is equal to y into derivative of log x is 1 upon x plus log x into derivative of y is dy upon dx. The next step, dy upon dx we can take as outside. So 1 upon y minus this log x will come to this side and become minus. So minus log x is equal to y upon x. Taking LCM, dy upon dx into 1 minus y log x upon y is equal to y upon x. Therefore, dy upon dx is equal to y square, cross multiplying y square upon x into 1 minus y log x. This is the final answer for this question. So, next topic is derivatives of parametric functions. Consider a function x is equal to cos theta, comma y equal to sin theta, 0 less than or equal to theta less than or equal to 2 pi. Here x square plus y square is equal to cos square plus theta plus sin square theta is equal to 1. As theta varies from 0 to 2 pi, that means one complete rotation, the point x comma y, that's equal to the point P is, instead of writing x comma y parametric form, we used to write in the place of x it is cos theta and in the place of y it is sin theta. So it describes the circle x square plus y square is equal to 1. So the radius of the circle is 1. Here theta is called the parameter. This theta is called the parameter here, and x is equal to cos theta and y is equal to sin theta are called parametric equations. If x is equal to f of theta, comma y equal to g of theta, then x and y are called parametric functions. So next topic is derivative of parametric functions. For that we have to start with the theorem. So the statement of this theorem is if x is equal to f of t and y is equal to g of t are differentiable functions of t, so that y is a differentiable function of x, and if dx upon dt not equal to 0, then dy upon dx is equal to dy upon dt upon dx upon dt. So proof of this theorem will start with uh, given that x is equal to f of t and y is equal to g of t. Let there be small increment in the value of t, say delta t, then delta x and delta y are corresponding increments in the form of x and y respectively. This is same as the previous theorems. So this part you have to write small increments that you can write as it is. As delta x comma delta y are small increments in the value of t, x and y respectively. So delta t not equal to 0, delta x not equal to 0. Now we have to consider delta y upon delta x as the ratio here. Note that delta x tends to 0 implies delta t tends to 0. So we are considering delta y upon delta x here. So we need to get this result in the format of dy upon dt. So we'll consider this ratio, and instead of writing d, you will write delta, that's it. So delta y upon delta t upon delta x upon delta t, where delta x upon delta t not equal to 0. Then taking the limit delta t tends to 0 on both sides, we get limit delta t tends to 0 delta y upon delta x. That means left hand side we are giving limit, right hand side also we are giving the same limit to the numerator and denominator. Since x and y are differentiable functions of t, we have limit delta t tends to 0 delta x upon delta t is equal to dx upon dt, and limit delta x tends to 0 delta y upon delta t is equal to dy upon dt x's and are finite. From 1 and 2, from this one and this equation number 2, we can write the numerator and denominator of the equation number 1 as dy upon dt upon dx upon dt. Since the RHS of equation 2 exists and is finite, since it is an equation, LHS also finite and exists. So the LHS of this equation, limit delta x tends to 0 delta y upon delta x, it can be written as dy upon dx. Thus the equation 3, this becomes dy upon dx. Left hand side also we can change with using the definition of derivative. Dy upon dx is equal to dy upon dt upon dx upon dt, where dx upon dt not equal to 0. So this is the proof of this theorem. Now some exercise questions are given to you. You have to solve it. Thank you.